So this parts idea is another way of tackling products or quotients when traditional U substitution doesn't work. So on your AP exam last year, if you had a product or a quotient, U substitution was the only thing that would work. They didn't give you anything that U substitution didn't work. You just had to figure out the U, but it would always work. In these kinds, they're still products and they're still quotients, but a traditional U substitution doesn't work. And so we called it integration by parts. This is the formula. It has a U and a V and a DU and a DV. And when we learned it for the first time, I gave you an organizer that you used to help keep everything straight. And we would put the U here, and we would put the DV here. And then from the U, we would find the du dx. And from the dv, technically it was a dv dx, we would find the v. So we were doing both. And the test we used, let me see if you remember this, was the Lippitt test. Okay? The Lippitt test helps you choose the best U that's going to make your process run the most smoothly. So there's sort of a hierarchy of functions that helps you work through those. L stands for logarithm. If you are looking at a product or a quotient, and any part of that is a logarithm, that should be what you choose as your U. And whatever's left, whatever you didn't choose, that automatically becomes the dv dx. If you don't have a logarithm, the next thing to look for is an inverse trig. So sine, cosine inverse, tan, cotangent inverse, secant, cosecant inverse. That would be the next thing. That automatically would become your U, and everything else would become the dv dx. What do you think P stands for? Polynomials. So polynomials are things with powers. They can be fractional powers too, though. They can be to the half power, to the 5/3 power. That counts as a polynomial also. Okay, so it'd be a power. E is exponential. And then your last choice, if nothing else works, you'd use the trig function. And so these are what you choose to go here in the U spot. And everything else that wasn't chosen is left to be your dv dx. Once you choose your U, we'll go back up. I just want to review with you. This is what you, no, I don't like that. This is what you start with. So you make your choice here. Okay, so you'll be given a problem. It'll be in the form of a product or a quotient. You make your choice for your U. Everything else becomes your dv. Then you reassemble the parts together in the following order. You're going to have the product of UV coming first. So a lot of times in the graphic organizer, we would look diagonally that we're going to choose the UV. And we're going to reassemble the parts, and those two go together first. And then you're going to subtract the integral of v du. So you look side to side here. You're going to subtract that integral. And what should happen is that the integral that combines to make should be something that you can integrate fairly easily. If not, you might have to do it one more time. That's repeated integration by parts. Hey, is that kind of looking familiar? Okay, we haven't done it in 7 months, but You've seen it before. Okay, so let's try. So you just have to recognize, okay, this is a product of two functions that follow the limit. I have a power. Okay, x is considered a power. It's power 1. And I have a trig. So according to the Lipit hierarchy, the x is what I'm going to choose as my u. So u is going to be x. That means everything else is left as my dx, and I'm going to do an integral on that. So from x, I find the differential, and the differential on x is dx. Don't put 1, it's dx. You're going to need the dx. And then on the other side, you're going to do the anti. And the antiderivative of sine of x is negative cosine of x. And now reassemble your parts to solve the integral. So as we reassemble, we're going to go diagonally first. So that will give me negative x cos x. And then minus the integral. And then we'll go across, combining my differential that I found for u and my that I found for sine of x. So that would be minus negative cos x dx. So that double minus becomes a plus. And so that integral, that second part, should have an antiderivative, and it does. And so we have negative x plus the antiderivative of cosine, which is sine of x. And then we have the constant of integration that came across from that. How would you check your work? Okay, re-establish what the derivative is using the product rule, and you should end up back where you started with x, sine x. Okay, any questions on that? Okay, so let's try another one. Okay, so we're looking at this. Natural log does not have an antiderivative that we know of, that we have memorized. It's not one of the ones that we have. But according to Lipit, natural log would be what I would choose for my u term. So I'll have the natural log of x, which means the only thing that's left is dx, which technically would have a coefficient of 1. So I work my way through the differentiation process. So that would be 1 over x times dx. And then I would take the anti-differentiation process, which is going to give me just x. And then I reassemble my parts, my puzzle pieces, to get me back with what the actual antiderivative natural log of x is. So I look at the combination. That would be x ln x. So that's my diagonal combination of x and v, u and v. And then minus the integral of the product of 1 over x dx and x, which is 1 dx. And that part should have an antiderivative, which is minus x, and then the constant of integration. And I could check that again. If I retook the derivative, that derivative should simplify down to just being ln x. Okay? Am I going too fast? Tell me to slow down. All right, here's another one. There's another one where you would choose. There is no basic antiderivative for log base 5. So we're going to choose log base 5 of x to be our u, which leaves 1 dx, okay, the understood coefficient of 1. Then I'll take my derivative, which is going to be 1 over x ln 5 times dx. And then my antiderivative, which is going to be x again. Okay, then we reassemble the pieces. So we have x log base 5 of x minus the integral of the combination, which would be 1 over ln 5 as a constant dx. And so since 1 over ln 5 is just a constant, then it's 1 over ln 5x plus the constant of integration plus c. Here's an inverse trig. We haven't done one of those yet. Well, we go through the Lippitt hierarchy. Since I have no logs, then the inverse trig is going to be my choice for u. Oops, x. And then 1 dx will be my, my other part. My differentiation process is going to be 1 over the rad of 1 minus x squared times the chain rule, and then multiplied by x. Reassembling the parts gives me x sine inverse of x minus the integral. Now, this doesn't reduce nicely. It gives me 1 over rad 1 minus x squared dx. So that integral, and specifically doesn't have a slam dunk integral that we know, but I can apply a regular u substitution to that. If I reinterpret that integral as x parentheses 1 minus x squared to the negative half dx, I can use a second substitution. I might use so I'm going to use 1 minus x squared to be my u for this, the work I'm doing this time. So negative 2x so the implication is that dx by itself would be du over negative 2x. So you're just doing the basic stuff we did before. So x sine inverse x minus the integral of x times the quantity u to the half, and then my differential substitution will be du over negative 2x. So that'll help clean that up quite a bit. So I can reduce the x's. I can pull negative 2 out to, or negative 1/2 actually, out to the front. So it'll be plus 1/2 times the integral of u to the negative half du. So then you're almost finished. So 1/2 u to the positive 1/2 times 2, divided by half, which is the new power, and then plus c. So putting everything together, you'll have the coefficient of half and the anti-chain rule of 2 reducing. So you're going to be left with the square root of what you chose for u in this part of the process, plus the constant c. Now let me make one other comment. If this had bounds, okay, if this had started with bounds of 0 to rad 2 or something like that, the bounds impact the entire process of the equation from the beginning to the end. So your brackets would include all of it and your bounds would get plugged into all of it if you had bounds. Then you'd be finding the area under the whole thing of the whole antiderivative. All right, last. This happens when you get down to the lower part of Lipit. What are the two categories here? An exponential and a power. Okay, so when you get down to a PET, those numbers down there, you're going to need to do integration twice in order for this to solve itself out. So we'll start with 2x squared, because that power is going to beat out the e to the x dx. So my antiderivative will be 2/3 x, sorry, not antiderivative, my derivative will be 4x, and then my antiderivative for x dx. In this case, I usually, because I kind of know what's coming, I start with the original problem first before I get going. So I'm going to have 2x squared ex, that's the first combination, minus 4x e to the x dx. So I recognize, shoot, I have a power and an exponential combination again. So I need to repeat the process. So this time I'll choose 4x and then have e to the x dx, which means my derivative is 4 dx and my antiderivative is e to the x. So this, in the second part of the process, as I put my parts together, I'll have 4x e to the x minus the antiderivative of plane 4 e to the x dx. But what do I have to watch that immediately preceded that? A subtraction. So this subtraction affects all of that. So I still have my 2x squared e to the x, but I have a subtraction that impacts all of it, and the subtraction is going to get distributed. So I will have 2x squared e to the x minus 4x e to the x, but plus integral 4 e to the x dx. And that last integral is possible to solve without having to do integration by parts. So that is 4 e to the x plus the constant of integration. All right, we talked too long about Catalina. I had one more to do. This is the last kind, when you have an exponential and a trig. And this one, we'll get as far as we can before the bell rings. This is going to cycle back onto itself. All right, so here's the question. And remember, e comes before t. So exponential first, trig second. At this point, we'll work through the differentiation and anti-differentiation process. So e to the x dx is going to be our derivative, and then the antiderivative would be negative cosine of x. All right, so then we work on putting those parts together. So pairing up diagonally, we're going to have negative e to the x cos x And then we're going to have a minus, but the double negative is going to make that a plus, e to the x cos x dx. So that leads us up to doing this process a second time, because we still have the combination of the exponential and the trig. So we'll choose that exponential again, and then have cos x dx as our leftover values. All right, so the antidifferentiation process, e to the x dx, and excuse me, derivative process, and then the antiderivative sine of x. All right, and so we are ready to work through the pairing up of parts again. So we still have the original negative e to the x cos x, plus the next part would be e to the x sine x, and then minus our final part of e to the x sine x dx. This is where we realize that we're encountering the same combination that we started with. So our original was also e to the x sine x dx. So we have what are called like terms. We've got the integral of e to the x sine x dx on one side, and then we have the minus integral of e to the x sine x on the other side. So this means that we can move the one integral over to the other. So we're combining like terms. So we're adding this e to the x sine x dx over to the other side. So that's going to give us 2 of the integral e to the x sine x dx being equal to negative e to the x cos x and positive e to the x sine x. And there is a constant of integration that comes as a result of all of the antiderivatives that we've been doing. So to solve for our final answer, we just need to divide by the coefficient of 2 so that we can have the integral of e to the x sine x by itself. And so we'll have negative e to the x cos x plus e to the x sine x plus the constant of integration all over the number 2. Sometimes you'll see that answer written this way, where the constant of integration is kept separate, and that constant is also divided by the number 2. But because you're dividing a constant by another constant, the result is still ultimately a constant, so you'll probably most likely see the answer written like that. A couple things to watch out for. If you have a problem where this term right here is a subtraction, you'll have to make sure that that subtraction is properly distributed throughout the remainder of the problem going to the right. So watch out for that. Other thing you will need to watch out for is if you have any kind of coefficient term. So for example, if the problem started out with a 2 here or a 3 here, you'll have to make sure that you are doing the anti-chain rule or the regular chain rule appropriately as you work through the integration by parts. That means you're going to have some fractions in your work. Okay? All right, working through this, and we'll see you guys back together tomorrow.